Let's discuss converting from revolutions to radians and from radians back to revolutions. So going around once, remember, in the unit circle is equivalent to 2 pi radians. So, or in decimal form, that's 6.28 radians. If, as an example, we want to convert from revolutions for each second to radians for each second, and we had a value like 10.0 revolutions per second, we would use 2 pi radians over 1 revolution to convert that to 62.8 radians per second. Notice that what we're trying to accomplish here is to cross out or to cancel the revolutions in the numerator here and the denominator there so that we end up with radians per second. Conversely, if we want to convert from radians for each second to revolutions for each second, and we take a number like 62.8 radians per second, we use the inverse of that same conversion factor, in this case 1 revolution over 2 pi radians, and that cancels out the radians, and we end up with back to 10.0 revolutions per second. Now realize that this is a conversion factor that you should know because of the math classes that you guys have had. Let's compare the center of mass displacement of a wheel, like this green wheel, moving along a surface, and the fact that the wheel is rolling without slipping. We're going to compare that to the arc length that the wheel is making contact with the ground. So notice that the displacement of the center of the wheel, this burgundy color here, is a certain distance from there to there. We also call that center the center of mass. And also notice that the arc length of the outer edge of the wheel is this blue line. It's the distance along the outer edge of the wheel that makes contact with the ground. Observe their values. At this point, you should be able to realize and answer the question, what is the relationship between the arc length of the outer edge, this blue outer edge length, that arc length, and the displacement of the center of mass, how far the middle goes. Let's look at how to solve problems with linear and rotational dimensions. This bicycle wheel here is accelerating from rest to 5 meters per second in 10 seconds. If the radius of the tire is 0.5 meters, we're going to try to figure out the number of revolutions made by the tire. In order to do that, we need our linear and rotational kinematics equations. We also need these bridge equations that take us back and forth between linear and rotational quantities. We need to also remember that the displacement of the center of mass of a circular object rolling without slipping equals the arc length of the outer edge of the circular object. And finally, we need to know how to convert from radians to revolutions and from revolutions back to radians. So just like we used to do in our linear world, where we looked at the linear displacement, velocity, and acceleration, we need to draw a motion map. We need to list the five kinematic variables in the linear dimension. We notice that V initial is something we know, V final is something we know, and T is something we know, and we're going to look for the acceleration. So we need an equation that has these 4 variables there, and it turns out to be that linear equation there. If we substitute in the equations, we then get an acceleration of 0.5 meters per second squared. Then if we want to know the displacement of the center of mass of that object, we end up using this equation because we have even more than 3 variables that we know. We have 4 and the one that we're looking for. So that's the equation that's going to work for us. We substitute in the values that we need, and we find that the center of mass displacement is indeed 25 meters. It ends up way over here at 25 meters. Let's look at the rotational motion. Just like with the linear motion, we need to draw a motion map in the rotational direction. We start off with our rotational displacement. It points in the clockwise direction, and we call that direction negative. The initial velocity is 0, and it increases in the negative direction, the angular acceleration is constant in the negative direction. If we want to convert this displacement of the center of mass, which we calculated to be 25 meters, we're going to need to use our bridge equation that shows that theta, if we want to find that value in radians, we take the 25 meters that the center of mass traveled and divide it by the radius to get negative 50 radians. So in other words, it spun around negative 50 radians of angle. To convert that to revolutions, and we can actually count that if we go 1, 2, 3, 4, 5, 6, 7, 8, we get about negative 8 revolutions. And the way we do that is we use this conversion factor where we put 1 revolution over 2 pi radians to cancel out the radians and get our negative 8 revolutions. And that, remember, we get from our conversion factor of 1 revolution over 2 pi radians. If we want to find the angular speed in revolutions per second, we would take the final velocity and use a different bridge equation and solve that for omega, and we would take our 5 meters per second divided by the radius to get negative 10 radians per second. So that's our final angular speed. Now, we could also convert that negative 10 radians per second to revolutions per second by using this conversion factor here, 2 pi radians divided by 1 revolution, and we get negative 1.59 revolutions per second. As some of you may have noticed, we didn't use any of the rotational kinematics equations, but we certainly could have. There are many different ways to solve these problems.